Okay, good morning everyone. Today's talk is about the isoperimetric inequality in the third-dimensional Heisenberg group. Let's start and remind some things from the previous talks. We are working in the third-dimensional Heisenberg group with x, y, and t coordinates. The horizontal subspace H is spanned by x and y vector fields. We follow the Capogna notation with the 1.5. We have the contact form theta, and t is the Rib vector field. And we also remind the formula for the left translations of our Lie group for two random points p and q is given by this formula here. And we also remind the exponential coordinates. We have the exponential map. So it takes a left invariant vector field from the Lie algebra, which is a combination of the orthonormal frame, x, y, and t. And the coordinates with respect to the orthonormal frame are called exponential coordinates. So we start with an open and smooth set omega inside the Heisenberg group, which is bounded by d omega, and we choose a point P in the boundary and the random direction angle theta in 0 to pi. And we define an horizontal direction, which is this vector field here in the boundary point, and it is a unit vector field. And we also define the first exit time as this. So practically, it's the time that a path that joins P with a point inside omega, then it escapes after this time. And because this vector field is left invariant, we can find its integral curves. These are of this form, it is known, that are starting at the point P, and the starting velocity is the vector field x theta calculated at P. And the integral curves are called the horizontal lines for this vector field. And also, for a general point now inside the Heisenberg group, we can define the canonical section at P as this set, sigma at P, is a set of all the horizontal lines that are going through P. And we can identify the R2 plane with the horizontal subspace at the identity. So we have this map here, the section map at P, that is defined via this formula here. And we can use the uniqueness and existence theorem for the integral curves. And we have this identification that the image of the R2 plane using this map is practically the space of all the horizontal lines through P. And these lines are forming the plane sigma at P. We can now choose a parameterization for this set for sigma at P using this map by these facts here. So for the sake of notation, we can replace A and B with the usual U and V coordinates for some parameterization. And we have this parameterization here for the plane sigma at P. We remind from a previous talk that the perimeter measure can be given using this formula. And when we choose a surface patch like this here, we can calculate the surface measure using the normal vector. So we have to express the normal vector with respect to the orthonormal frame, x, y, and t, but we have to remind that it is calculated at the point on the surface. So one can find that the two vector fields, here the tangent vector fields, with respect to u and v are these, and we can write the cross product with respect to the orthonormal frame x, y, and t, but calculated at the points of the surface. So we can substitute everything back in this formula, and therefore the surface measure can be given using this type here. We can make a substitution to a change of variable to polar coordinates here, and we can express the perimeter measure to polar coordinates on the plane. Our main theorem for the road to prove the isoperimetric inequality in the Heisenberg group is this, that we start with a domain D, or a smooth domain in R2, bounded here, and we choose V smooth surface and we choose V set in the Heisenberg group, and which is a smooth surface with a boundary, the image of sigma of the boundary of D using the map sigma at the identity. So we have that is a minimizer for, we will prove that this set here is a minimizer. The set sigma 0 at D is a minimizer for the perimeter area, and we'll use the calibration method like Ritorri and Rosales. Here we have a geometric depiction of the theorem. We start with the domain D. This is its boundary inside the R2 plane. We use the map sigma 0. So we have a competing V with boundary the set this set here. We have to remind that for a random surface, the horizontal perimeter is calculated using the perimeter measure we have mentioned previously, and our goal is to construct a horizontal vector field which has unit a unit meter norm. So and that it has to hold this equation here. We can express this image here, the image of D using sigma 0, let's call it M, which is a submanifold of the plane T equal to 0, and we can write it as a level set, and the local defining function is F here. So this equation holds for the boundary using the diffeomorphism, practically, sigma 0. We can calculate the horizontal gradient of F and the horizontal unit normal. And we can see that the horizontal mean curvature, which is the horizontal divergence of the horizontal unit normal, is equal to 0. So we have that sigma 0 and the set M practically are area stationary points for the horizontal perimeter. So we have then we consider the foliation by planes of this form here that are perpendicular to the t-axis, and these planes are the leaves of the foliation. So we have that the characteristic set is this, let's call it C, that are the points in the t-axis there. So then we define a horizontal unit field, this U that will make all the work here. U is defined using this formula, and we have to see that U is equal to the horizontal unit vector, which is practically the same calculated at all the leaves. And then we can choose as omega the third dimensional set, which is enclosed by the competing set V and M, which is the base. We will see then an image. M is the base of and the boundary. Then the boundary of omega is has two connected components, V and M, and we can choose a cylinder, practically the interior of the cylinder here for a random radius, which is positive essentially. And we define these sets. The boundary decomposes as we can see here, and these sets are the intersections of V with of V and M with omega r here, and we define the cylinder CR, which is the intersection of the set omega with the cylinder. So practically we have a set which has three sides, let's call it this surface. We can use the Gauss divergence lemma, and the integral with the divergence is equal to 0 because the divergence with respect to the metric, to the Riemannian metric we use, is practically the horizontal divergence of U, the calibrating vector field. So the integral at the boundary has the composition here using the orientations that we want. And since U is a unit vector field, we can use the Cauchy-Schwarz identity, and we can see that taking r to 0, this integral here is practically 0. We can take the limits for r to 0 in the Gauss divergence theorem here, so we have the equality of these two integrals. And we remark that because U is an horizontal vector field, practically the product of U with n is the product of U with the horizontal component of n. We can use the Cauchy-Schwarz identity, and we have this inequality here. And then we integrate both sides with respect to ds, and we have that this inequality here holds. Then on the base manifold, which is the base of our region, here we can see that u is equal to the horizontal normal unit vector, and then because of the definition of the horizontal normal unit vector, this product here is practically the norm of the horizontal component of the normal unit vector n to the surface, and we can combine everything here using this equality and this fact, and we can see that m practically is a minimum. Then we can continue to our main goal, which is the proof of the isoperimetric inequality in the third dimensional Heisenberg group. We start like previous with omega, an open set bounded by d omega, and we take also a point in the boundary. We can define this set here, P at P. So we have, which is an open subset of the plane sigma at P, which is the image of the section map, as we mentioned previously. And then by the definition, we can parameterize the boundary of this set, and we can see that here we have the first exit time practically for this curve, which is a one-dimensional manifold. And this curve splits the boundary of omega into two connected components. Let's call them V1 and V2. So this equality here holds for the perimeter measure using the decomposition of the boundary of omega here. And then we can express d as the preimage this set that we defined using polar coordinates. And one of our lemmas says this, that in the notation established above, we have this equality of integrals here. We have that in this integral, we have the horizontal area measure, which is expressed in polar coordinates, like this expression here. And we return back to the lemma. We choose a point P in the boundary, and we can use polar coordinates. Then we can see that here, because of the equality of, because of the formula of the perimeter measure in polar coordinates, we can integrate with respect to omega this equality, and we have the identity one here for the lemma. Also, we will use this fact that if we have an Euclidean ball centered at the identity with radius r, and let's call its volume vol d, and we have an increasing function, then we have this inequality for the integrals. We will use this inequality, this lemma here for n equal to 2, and our set D is practically the preimage of this region here using the section map at the point P in the boundary. And this function here practically is the function 1 divided by, let's call the variable t. So t is practically the norm of u and v. we apply 2 times the previous lemma, and we will use the fact that because this area, this plane, let's call it this area of the plane is sigma at p, the Greek p at the point p, is the boundary practically of the image of the boundary of D using the section map. We will use the main theorem here because practically has the same boundary, and using the left invariance of the perimeter measure, practically the perimeter of sigma, the perimeter measure of sigma at the point P of D is equal, using a left invariance, to the sigma 0 of D. And then we can add both sides of this inequality here, and it follows that we have the following lemma after these facts. And we will use a Santalo type formula here, which is the main tool for the proof of the isoperimetric inequality in the Heisenberg group. Also, because the vector field x theta at p is unit, and also because the horizontal normal is a unit vector field, we will use the Cauchy-Schwarz inequality and the identity one, which is here by our lemma, and then we have and then it will lead to the isoperimetric inequality in the third-dimensional Heisenberg group, which is this inequality, the volume of omega, and here it is the volume of omega, and we have the perimeter of omega. Santalo type inequalities equalities